Okay, so yesterday we were doing Dirac Delta function, and today we shall finish this topic so that we are going to move forward in the quantum mechanics side. Okay, so yesterday we were doing a function called a sinc function, and we were trying to write the limiting case of the sinc function, as a Dirac Delta function. And just to make you realize that we were not able to derive it, so it's better to just intuitively understand how would it behave. Okay, so this was the sinc function. If I clearly remember that this was the function. Okay, so this was the function sine nx divided by pi x. Okay, so to make a to make the right plot, you should either use MATLAB or Mathematica, or you can go on to your I think there are many simulators on even web page online also. So you can plot this up and you can see what we are doing. So as you can see, 1 over x already goes towards 0, isn't it? 1 over x is something that already goes towards 0 as x tends to infinity. Okay, so how does the 1 over x behave? 1 over x will go this way only. Okay, now understand my point that the amplitude of the sine. So amplitude of sine, what will it do? It will try to oscillate around. This amplitude, and amplitude itself is a function of x. So as x tends to infinity, this amplitude will eventually die out. So you can see that this will be an oscillated function for sure. Sorry. And as you will see that around x equal to 0, there would be a peak, and then it will eventually die out again. Okay, so what does Dirac Delta function say? So for example, what does Dirac Delta function says? Dirac Delta function says that if I am having a Dirac Delta function stationed at x equal to 0, it means you will have a narrow infinite spike over x equal to 0, and all over you should have 0. So for all x not equal to 0, your Dirac function should give you 0, and exactly at x equal to 0, your Dirac function should be infinite. And this is your Dirac Delta function, which is stationed at x equal to 0, or which is situated at x equal to 0. Okay, so overall, try to make a grasp of it that if at all this function is there. So for example, this function is sine x. Now try to understand my point that as x tends to 0, this entire function will become like sine nx upon n you place here, and you write n upon pi. And we are trying to find the limit of this particular function as n tends to. So you keep x tends to 0, that is absolutely fine. So as x tends to 0, this particular thing will become 1. That is absolutely fine to you, because this is limiting case. X tends to 0 means nx also tends to 0. So sine nx upon nx, and this will go towards. Remaining, you have this particular portion. So as x tends to 0 and as n tends to infinity, this will approach infinity. So what is happening is, in this particular for this particular function, as you're approaching closer to the 0, and in the limiting case n tends to infinity, this is eventually becoming a narrower infinite spike. Okay, can you understand my point? I mean, this is what it is happening. Like for example, if you see that as x tends to 0, what will happen? As x tends to 0, this will become 1. And overall, you can understand that because we are trying to find the limit of limit n tends to infinity del nx, so we are actually trying to find how this limit of these sequence of function would be here. So basically, this is sequence of function. You should understand this is sequence, because here there is you can find there is an n. So n belongs to natural. For different other natural numbers, you will have different values. So this is a sequence of function whose limiting behavior we are studying as n tends to infinity. But again, while studying the limiting behavior, you should keep some eye. You have to keep an eye at x. So if x tends to 0, as x tends to 0, this would become 1, and as n tends to infinity, this would go towards infinity. So basically, what is happening? As x tends to infinity, your n tending to infinity would make it peak around x equal to 0. This is clear? Around x equal to 0. Okay. Overall, you have, because the derivation part is quite you can say very rigorously mathematical. So I'm not going there. Just trying to make you understand that possibly in the limiting case, it will behave as if it is a Dirac Delta function. Okay. Further, also understand that these points, just try to locate these points. What are these points? These are those points where sine nx would be 0. So your sine nx would be 0 when your nx would be equals to 2 pi. So your x will be 2 pi over it. You just see all these values. I mean, all these roots can be written as 2 pi over n. You can just place. Now see, as n tends to infinity, all these points are actually shifting towards origin. You can understand, as n tends to infinity, all these points are eventually shifting towards origin. So basically, these are all you will find that if you start plotting this function on your MATLAB or somewhere in some simulator, you'll find that if you increase your n, then soon what will happen? This will start getting concentrating over around origin, and all these things will start fading out. So in the limiting case, as n tends to infinity, the area under all these plots will start becoming 0, and eventually you will be getting a narrower infinite spike at around x equal to 0. So this should give you enough motivation that this particular function in the limiting case would behave as if it is a Dirac Delta function. So this is one other representation of writing Dirac Delta function. So this is yet another representation of writing Dirac Delta function. Is that clear to you? Am I audible?
भैया एक बार बताओ ना प्लीज.
हाँ, क्या बोलूं?
एक बार बताओ ना वापस से nx upon nx.
अच्छा, ओके. सो देखो
सर, इसमें हमने
हाँ
सीक्वेंस क्यों लिया है?
हाँ, बोलो प्लीज, बोलो क्या कह रहे हो?
सर, इसमें हमने सीक्वेंसेस क्यों ले रहे हैं? हम सारे फंक्शंस में नॉर्मल फंक्शंस क्यों नहीं कंसीडर कर रहे?
ओके, उसका आंसर ये है कि बेसिकली जब तुम ये जनरलाइज फंक्शंस बोलते हो ना, ये जनरलाइज फंक्शन का मतलब ही होता है कि द फंक्शंस व्हिच कैन बी रिप्रेजेंटेड एज द लिमिटिंग केस ऑफ द सीक्वेंस ऑफ फंक्शन. दिस इज हाउ इट इज एक्चुअली डिफाइंड, मतलब
ओके
मैथमेटिकली.
ओके.
So what we'll would do, or and secondly also understand what function can you take. I mean, देखो मेरी बात समझने की कोशिश करो. Dirac delta function जो है, it is saying कि you have an infinite contribution at a point, and otherwise you don't have any contribution. And this contribution can have many other physical contexts. So, for example, if I'm writing a point charge, it has a context in writing the volume charge density. If I'm considering point mass, then I'm saying about mass density. Or possibly if I'm writing an impulse force. So for example, I'm saying a force acts for infinitesimal small second tt. Let's say, for example, if a bowler is bowling a ball and it hits the bat. So basically there is only a t tending to 0 kind of thing. So basically this is an impulse force, which is actually imparting the moment into the ball. So possibly I can write this kind of thing in Newtonian mechanics also. Okay. So there are many instances where you would find all these things. So basically it may have different sort of physical interpretations, but try to understand there would be no such function till now, well behaved or conventional, whatever you know till now, which would actually correspond to this. Because here it is saying you have to be a 0 at a point, as you have to be infinite at a point, and then you don't have any value. So how would this be? It says that for all these values of x, you have only one value of one value, that is 0, and otherwise it has only one single value, and that is infinitely large. What sort of function would correspond to this? I don't believe that there is any sort of any function that you studied till now which corresponds to this. So mathematically, this is a rigorous case, and you should understand this. This did not appear to mathematicians at first. This appeared to physicists at first. You have this book called as PAM Dirac's own book, that is quantum mechanics. So
yes, sir.
So basically, this is the book by legendary himself. So point is this: he has written all these things. Basically, this was not even in mathematics at first. This is what I know. So basically, no doubt, mathematics has a rigorous theory on generalized functions, and they do all sort of things. But right now, we have to understand our point with regards to physics, physical insight. So you don't have any such representation. So what do? You try to make some functions. For example, I made a function which suggests, okay, हम लोग -1/2n से लेकर +1/2n के बीच में we'll try to make a n. Then again this. So basically what we are doing in the limiting behavior, we can see that we are approaching as close as possible to x equal to 0, and we are having an infinite spike here. So that is one thing. And also that if you read the generalized function definition also, you'll find that a sequence of functions is required there. So I'll come to this particular point only if you are quite motivated to do so. But otherwise, overall, try to take the physical insight out of it. And now coming to Alpana's question, what she says is repeating all over again. So I'll repeat it. This is sinc function. It suggests that sine nx upon pi x is one function. I'm saying the limiting case to this function would be a Dirac Delta function. So basically, if I say that limit n tends to infinity del n x, it implies that I'm writing some Dirac Delta function. Okay, so this is one thing. How would I do so? So I told you that this particular graph, if you try to simulate on your internet or somewhere like Mathematica, MATLAB, somewhere, so you'll find this sort of thing. Okay, so this you can actually plot yourself also, because what I want to say is कि होगा क्या? What will happen is, देखो इसका जो amplitude है, that is pi 1 upon pi x, and this is sin x. So this will be an oscillatory term. This will be a term which is amplitude, and amplitude itself depends on x. So as x tends to infinity, you can clearly see that your amplitude should tend towards zero. But although because sine is there, so it will envelop itself into some oscillatory kind of thing. So basically, no doubt this like होता क्या sin x में क्या होता है? What does happen? What do you see in sin x? Sin x is a graph where you have constant amplitudes, +1, -1, +1, -1. But here, in the case of amplitude, you can see that there is 1 upon pi x. Now, as x tends to infinity, you can see that these oscillations which eventually die out, because this the amplitude term itself is tending towards zero as x tends to infinity. So you can see this would be the graph. And more often you'll find these things in diffraction theory, or possibly in time-dependent perturbation theory. Time-dependent perturbation theory. So we'll see in both of the cases this kind of function, that is sin x over x. Okay, but overall try to understand this point. Now see, as n tends to infinity, you will be seeing that there can be two cases. One case can be that, let us understand if x tends to zero also. So if I'm talking about close neighborhood or your close vicinity to x equal to zero, what would you find? I'll write this way. I'll write this way. I'll write this. Okay. Now see, in the closer vicinity to x equal to zero, you'll find that this case will be a limiting case of x tends to zero, and this will go towards 1. So I'm saying if I'm sufficiently close to zero, this limit would become 1. And overall understand that if I'm trying to find n tends to infinity, this will go towards infinity, because this is 1, n upon pi, n tending to infinity, overall this will become infinity. So I'm interested in finding the limit, and as I'm finding the limit, I will be questioning myself, what are the values of x? So if x is closer to x equal to 0, there would be an infinite kind of value that it will take. Okay, and overall understand, for all those terms which are not close to 0, in fact, you can see as x tends to infinity, it's very much clear that as x tends to infinity, this is sine nx, and this is pi over x. So sine nx would remain between -1 and 1 only. Even as large as you may take x, sine being an oscillatory function, sine will always remain between -1 and 1. And this particular function, 1 upon pi x, will blow up. So overall, for large values, it is quite clear that sine nx upon pi x, irrespective of what your n is, it will tend towards zero only. So eventually these oscillations will fade out. But try to understand how to make you realize that for all x not equal to 0, all x not closer to 0, it will eventually die out. For that, I'm saying, just understand that these roots, you can see that these roots kahan pe honge? They will be roots where sin nx would be 0, that is nx should be equal to 2 pi, that is x should be equal to 2 pi upon n. So you can see that these all points, these roots can be written as 2 pi upon n. So the set of all roots would be 2 pi upon n, or you can say some non-zero integer. So a non-zero integer. Okay, so n belongs to non-zero integer. So you can see this will be 2 pi, this will be 2 pi upon. So are you getting my point? So now understand, if I'm taking n tending to infinity, if I'm taking n tending to, 2 pi k upon 2 pi k upon n, where k belongs to z. So now you see, as n tends to infinity, this entire thing will go towards 0. 2 pi k upon n, this entire thing will go towards 0. So you can see that all these roots are eventually fading out as n tends to infinity, and we are actually approaching 0. So these roots fading out means you are actually coming closer and closer to origin. And you are getting, the amplitude is increasing. Okay, are you getting my point? Is that clear to you? I mean, what I'm trying to say is कि जैसे जैसे हम लोग अपनी n टेंस टू इन्फिनिटी करेंगे, वैसे वैसे ये जो रूट्स आ रही है ना 2 pi upon n, 2 pi k upon n टाइप की, ये फेड आउट होना चालू हो जाएंगे, and you will have very little oscillations about points which are not close to 0. Basically, all these terms, as you keep on increasing your n, these will eventually fade out. So basically, it will look like this kind of behavior, and then you'll have an infinite spike, and then you will have some oscillations. Now you keep increasing your n, and you'll find that this will perfectly start matching towards Dirac delta function. So I want to assert my case that if this is the function that is sin nx upon pi x, and this is called a sinc function, if I take a limiting behavior as n tends to infinity, I would get a representation closer to Dirac delta function. Is that clear to you? So you just correct it. It was not 2 pi upon n, right? 2 pi k upon n, sorry. This would be no doubt because here k is 1. So this would be, in general, I can write roots as 2 pi k upon n. Are you getting my point? So because sin nx 0 kab hota hai? Sin nx 0 hoga when nx is equal to 2 pi n की जगह लिख देते 2 pi k. So x क्या हो जाएगा? 2 pi k upon n नहीं हो जाएगा. अब सोचो n tends to infinity पे क्या होगा? ये सारी रूट्स किधर की तरफ शिफ्ट होना चालू होगी? 0 की तरफ. तो बेसिकली ये जो ऑसिलेशंस जो अभी तुम्हें ब्रॉड दिख रहे हैं, मतलब कुछ एरिया दिख रहा है, धीरे धीरे दिस एरिया विल स्टार्ट फेडिंग आउट, एंड you will have an infinite spike around x equal to 0, infinite spike around x equals 0. Is that clear to you? तो गलत समझ में आया?
हाँ जी सर. सर डिस्ट्रीब्यूशन और
हाँ बोलो, सॉरी.
डिस्ट्रीब्यूशन और फंक्शन में एक बार डिफरेंस बताएंगे?
ये मैं तुम्हें बताऊंगा, एक बार मुझे थोड़ा सा टाइम दो, ठीक है? बिकॉज ऑल दीज टर्म्स आर थोड़ा सा डिफिकल्ट, मतलब मैं चाह रहा हूँ इनको मैं रिग्रेसली ही पढ़ा दूं. व्हाई शुड आई राइट एनीथिंग एल्स? तो अभी के लिए ऐसा समझो कि बिकॉज you cannot define such thing. इनको distributions ही बोलेंगे. I'll write a better definition to it. Don't worry about it. ठीक है? Don't worry about it. I'll write a better definition. Okay. So this is a Dirichlet integral that you are actually all these functions, all these things would require me to actually teach you generalized functions. So I'll take a lecture. Don't worry about it. I'll keep that in advanced topic because not many people are interested there. So overall, let us first do this. Then we'll do generalized theory and also see what are called as distribution. In fact, we will also see what are distributional derivatives. So for example, if I say in your ordinary calculus class, if I had to say what is greatest integer function, so you'll say this is my greatest integer function. I think everybody knows about greatest integer function. If somebody does not know, just try to understand. I hope you're aware. This is greatest integer function. Is that clear? And you know that as x lies between 0 and 1, this would be 0. As x lies between 1 and 2, this would be 1. As x lies between 2 and 3, it would be 2. So you can see that there is a jump discontinuity at x equal to integers. Is that clear? Now you'll find, in fact, in TFR also they have asked this particular question: d by dx of greatest integer function, and everybody was in spellbound. कि यार इसको कैसे लिखना है? How to write? Right? How can you write? See, you can write that the derivatives are 0 because all these lines are parallel to x-axis. So derivative is equal to slope of the function at a point. So you can write the values of the derivatives here. That is 0. But you cannot write the derivatives here because here you have a jump discontinuity. So here you have to take the case of, you have to understand something called as distributional derivatives. So you can write the derivative of this particular function in terms of a distribution that is again Dirac delta function. So all these things I'll come at a later stage with you all, because this will be quite difficult for you right now to understand. But overall, try to understand my point that this particular function, that is sin nx upon pi x. I'll come to your point. Distribution and generalized function we'll separately study so that it becomes quite clear to you. Okay. 0 to infinity sin x upon x dx is equals to pi upon 2. This is Dirichlet integral. This we have already done through our contour integral. This was the first indentation that we studied. That is, in order to exploit this, in order to find this integral, we actually indented the curve around origin and we took an upper half of the semicircle and all those things. You know, this was epsilon, this was r, epsilon tending to r tends to infinity. So you can take this particular thing right now as a standard integral. And this we've already discussed. So minus infinity to infinity sin x over x dx would give you pi. Okay. Now try to understand my point. What was another property of Dirac delta function? Dirac delta function suggested that minus infinite to infinite Dirac of x dx should be equals to 1. Is that clear to you? So if that equals to 1, what does that require? What does so it requires that my function from minus infinite to infinite sin nx upon pi x dx should also be equals to 1. Is that clear? Okay. So now let us write sin nx upon, let us write sin here. Here you will have n, and here you will have 1 upon pi. minus infinite to infinite dx. Okay, is that clear? Now write nx is equals to y. If you write nx equals to y, then your n dx would be equals to dy. So I think this particular n dx will become dy, integral from minus infinity to plus infinity sine by dy, and then you have 1 over pi, and then this will be equals to 1 over pi into pi, and this will be equals to 1. So overall, it satisfies all the desired properties of the Dirac delta function. Therefore, I can suggest that this particular function given by sin nx on pi x, which is a sinc function, you can find it in literature, and there are umpteen other ways. You can go to Math Wolfram, and you will find that there are multiple other options to write all these Dirac delta function, which I'm not right now interested in. Right now, my only interest was to just make you understand that these are in general generalized function, functions which can be represented as a limiting case of the sequence of some functions. So basically, that is called as Dirac delta. And we'll come up to we'll study the theory of Dirac delta, generalized function later on, and we'll understand what generalized function very rigorously are. Okay, but overall, try to establish a picture in your head, because this is something that we're going to move along. Okay, one thing that we have studied throughout is one एक चीज जो हम लगातार देख रहे हैं, and which will motivate me to write this particular property. The first property that I would write is, see, the first property is, you can understand clearly that that all these functions, for example, from the day one when I started the lecture, for example, probably the first function that I wrote was this. This was, I think, e to the power minus modulus of x upon epsilon divided by 1 upon 2 epsilon. And I also shared Balkrishnan's lecture yesterday. I mean, I don't know, some article in the Resonance magazine, which also had some kind of representations like this. So Balkrishnan likes to write it in this fashion. He does not like, like he has written in his essay like this way. So this is also fine. Okay, this is also fine. No issues about it. So he has written that this will correspond to a Dirac delta function, absolutely fine. Okay, so you can clearly see that these families of exponentials would eventually peak around x equal to 0. Okay. Another function that we studied was Lorentzians. Then we studied Gaussians, family of Gaussians, and all those sort of things. Okay. Then we studied sin x over x, and all those things we've studied. Okay. From all these curves, you can find one thing. These are all symmetric curves. You can see they have all symmetry about x equal to 0. Where your Dirac delta function was there, you can see that all these functions are actually nothing but they are stationed at x equal to 0. All these functions are actually having a peak around x equal to 0, but they are actually symmetric. So first property is that Dirac delta function is a symmetric function. The Dirac delta function is a symmetric function. So Dirac delta function is a symmetric function. Are you getting my point? So what I want to say is that if I write Dirac of x minus x naught, or if I write Dirac of x naught minus x, they are one and the same. Is that clear? Okay. Now another property that I would write is, if I want to write what will be, another thing that I want to tell is, let's say what can be the discrete analog to your Dirac delta function. So discrete analog to Dirac delta function would be a Kronecker delta. So Kronecker delta is again a selector function. Selector function means what it will do, it will actually filter out a point. So for example, if I'm considering a set A, which is some A1, then A2, A3, AI, and then you have AI plus 1, then you have AN. And if I say just find me AI, what you would do, you would simply sum AI, multiply with this Kronecker delta. Because see, this Kronecker delta would survive only if your j is equal to I. So if your j is equal to I, then it will be 1. And if your j is not equal to I, then it will become 0. So for example, if j is equal to 1, this will be 0. If j is equal to 2, again this will be 0. Eventually, only if j is equal to I, this will give you a 1. 1 into AI is AI. You have to sum it all over. Although all the other terms would be 0, so you are left with AI. Okay, so basically what it has done, if I have multiplied this entire thing with this, and I have if I have summed all these all these quantities with j belongs to n, what I have found that I have filtered out AI from this particular sequence of numbers. Okay, a similar property would find in Dirac delta function, which you can see is a continuous analog to Kronecker delta, where if I have to filter out my function at a point, and let's say this is the case, then I will simply say this is equals to f of x naught. Okay, so this is f of x naught. Why this is f of x naught? You can clearly see that Dirac of x minus x naught would only exist if x is equal to x naught. Because if x is not equal to x naught, this would become 0. At x tending to x naught, or you can say as x equals to x naught, this no doubt would be an infinite case, but understand that minus infinite to infinite, Dirac of x minus x naught dx would be equals to what? Would be equals to 1 exactly at x equal to x naught, because for all other points, the area would be 0. So only area that exists is here. So this area would give you 1, and at x equal to x naught, your function will become fx naught. So remember, this property is your filtering property. So it filters out the value of the function at a point. Is that clear? Is that clear? Should I explain it all over again? Or is that clear? Should I move ahead? Okay. Now let us move to another property which says that, okay, let me write it. So that is called a scaling property. So what is scaling property? So all these properties I'm not deriving, I'm just writing it because hardly would take you a single minute to write the derivation of all these properties. So this will be equals to 1 upon a. So you can take mod a Dirac of x. Okay, so what does it do? If I'm not writing Dirac x, and if instead I'm writing Dirac of ax, it will be equals to 1 upon modulus of a Dirac of x. So you can do it very easily. You can simply take ax is equals to, and okay, whenever you have to derive some properties of Dirac delta function, try to utilize integration, because you can see that try to utilize integral. So whenever I'm telling you to write a property and derive a property, try to use integral, because you already know that minus infinite to infinite f of x Dirac x dx is equals to f of 0. So at least you know this particular property, and by knowing this particular property, you can do a lot many things. So for example, if I'm trying to explain this property for case a greater than 0, what it will be? So Dirac of ax, you can write f of x, and you can try to integrate from minus infinite to plus infinite. So if you do so, what it will be equals to, if you take ax is equal to, let's say, y, so it will become minus infinite to plus infinite, and here you have f of y upon a, if I'm not wrong, because x is equal to y upon a, and then you have Dirac of y dy. Okay, in any case, I mean, if a is positive, x tends to infinity, this will be infinity. As x tends to minus infinity, this will be minus infinity. So the limits of integral would remain same for y also, but overall this will be the structure. Understand my point here? यहाँ Dirac delta function कहाँ पर है? At y equal to 0. So what it will give me? It will say कि जहाँ पर भी argument लिख रखा है function का, वहाँ पे just place a 0. So just try to write a 0 here. So this will become f of 0. Okay, but this dy would be dy upon a. Because you see x is equal to y upon a, then I can write dx is equals to dy upon a. So you can clearly see that this is dy upon a, so this will give you this result, f0 upon a. Is that clear? And f0 you can again write in this particular way. So minus infinite to infinite, f of x Dirac ax dx can be written as minus infinite to infinite, and you can just place inside this f of 0, you can write f of x into Dirac of x divided by a. So you can compare these two things. So you can, after comparing, you will write Dirac of ax would be equals to Dirac of x divided by a. Similarly, this step can be written for a less than 0 also. So for a less than 0, the only one amendment that would be there will be on the limits of integral. So if I write minus infinite to infinite, f of x, this is Dirac ax dx, then this will be f of y upon a, then this will be Dirac of y, this will be dy upon a, and this will be from infinite to minus infinite, because now your a is less than 0. So these limits would change. If these limits would change, if I have to write from minus infinite to plus infinite, this will become f of 0 divided by minus a. Okay, if you just find this integral from minus infinite to infinite, now instead of infinite to minus infinite, write minus infinite to plus infinite, there will be a negative outside. So I'll write this way. So what it is equals to integral minus infinite to plus infinite. This is f of x, Dirac of, I think, x divided by minus a, and then you have. So if a is less than 0, then your Dirac of ax is equals to 1 upon minus of a Dirac of x. And understand my point. If I have to write this cumulatively, so for example, I have written, I'll again rewrite it for you. So if I have to write the definition of modulus of x, so modulus of x is what? Modulus of x is x. If x is greater than 0, it is equals to minus x if x is less than 0. Now, if I have to write Dirac of ax, this is written as 1 upon a Dirac of x if a is greater than 0, and it is equal to 1 upon minus a Dirac of x if a is less than 0. So clearly, if x is less than 0, if I'm writing minus x, if x is greater than 0, I'm writing x. Basically, what I'm writing modulus of x. So Dirac of ax can be, in short, can be written as this. Dirac of ax can be written this way. Basically, I've scaled it. So this is called, sometimes you find in literature or books, called a scaling property. Is that clear to you?
Yes, sir, clear.
अब लोग समझ में आया कि ऊपर से चला गया. अब लोग समझ में आया नहीं है. बोलता ही नहीं कुछ. चलो कोई बात नहीं. Are you getting my point till now?
हाँ जी भैया.
Okay. Now let us come to a point which is these days I'm finding in examination quite many questions are asked around this concept. And this concept says that instead of Dirac of x, if I'm replacing it Dirac of g of x, that is, in the argument of Dirac delta function, instead of x, I'm finding some function g of x. Okay, instead of finding x, I'm finding some क्या कह सकते हैं, instead of x you have argument as g of x, then what is the expansion? Yeah, what is the right expression of Dirac delta function? So what you can do, you can simply expand your gx in the neighborhood of x equal to xi, where xi's are the simple zeros. First thing that you have to see, that this particular function should have only simple zero, not repeated zeros. Like I've already taught you simple zeros, and again I will tell you x equals to x minus 2. अगर ये तुम्हारा function है, then x equal to 2 is a simple zero. If x minus 2 का whole square दे रखा है gx, then gx has a multiple zero. In fact, the root of multiplicity is 2. And I've taught you how to write these, how to tell about how to say that your function has a root of multiplicity m. In order to see that, you just see that if I'm saying my alpha is the root of multiplicity m, then your g alpha should be 0, your g dash alpha should be 0, and g m minus 1th derivative at alpha should be also 0. And for all other higher order derivatives, it should be non-zero. So for example, if I say x minus 2 ka whole square, this particular function has a root of multiplicity 2 at x equal to 2. What does it mean? It means f of 2 should be equal to 0. Try to find the derivative. F dash 2 would be equal to what? 2 times x minus 2 at x equal to 2, obviously 0. But f double dash 2 will never be equal to 0. That would be equal to 2. Certainly this is non-zero. So if this is the case, if I'm saying my function has a root of multiplicity 2, what does it mean? It means your function should be 0 at 2. Your function first derivative should be 0 at 2. Your function second derivative must not be equal to 0. This is in a way we can define the repeated zeros. Although I'm writing here that if I find a question, or if I find an inquisition which says that instead of Dirac of x, I'm writing Dirac of g of x, such that g of x has simple zeros. Are you getting my point? I'm not talking about these things. I'm not talking about the you can say repeated. It can have multiple zeros. I'm not saying that. I'm saying it should not be repeated twice. It cannot be repeated zeros. So for example, if I have again, I'm coming back to the point. If I have to write what is Dirac of gx, provided g of x has simple zeros, and let's say those zeros are given by zi's, xi's, then what to do? What I would do is I would simply take a Taylor series expansion of gx around gxi. So it will be gxi and x minus xi. And then I have, I think, g dash xi and dash dash dash. Obviously, you can see that if I have a simple zero at x equal to xi, the derivative of the gx would not be equal to 0. Because if at all it was a multiple 0, then the derivative would have been 0. But if I'm saying that it is a simple 0, then g dash xi would be non-zero. Is that clear to you? And if I take the leading term only, like leading term means, since you can see that gxi would be 0, so gx would be equals to what? X minus xi, g dash xi. So if I just take the leading term in the expansion, this will be the case, this will be the expansion. Is that clear to you? And if I have to write Dirac of gx, now I'll write Dirac of gx is equals to Dirac of x minus xi into g dash xi. Okay, so you can clearly see that instead of having written Dirac of gx, now I can write, and all these xi's can be like x1, x2, x3, xn. Understand, these are multiple zeros. These are not root of multiplicity. Understand my point? Like, say for example, if I'm saying sine x equal to 0, it implies x is equal to 0 is a root, 2 pi is a root, 4 pi is also root. All these are simple zeros. But if I say sine x square x equal to 0. Now x equal to 0, x equal to 2 pi, 4 pi, all are zeros, but they are repeated zeros. I'm not talking about these cases. I'm talking about these cases where I'm only considering gx being a function which has only simple zeros, and those simple zeros are given by xi's. What I would do, I would simply take a leading term of the Taylor series expansion of gx around x equal to xi. So gx will be equals to x minus xi, g dash xi. This is what I have written here. And you can clearly see that I have written a property Dirac of ax is equal to 1 upon mod a, and then Dirac of x. So instead of all these things, you can write 1 upon g dash xi mod Dirac of x minus x. And here xi can be different other things. So you can write m if m is the number of the possible. I'll come to it, don't worry about it. So you have to remember this particular formula. I have given you the motivation to find a right, but this is the motivation. This is how we do. So if I have to write Dirac of gx will be equals to 1 upon g dash xi mod Dirac of x minus xi, where gx is a function which has simple zeros at x equal to xi. Understand, it will not mean anything. Just write as a point here, it will not mean anything if gx has multiple roots. If gx has repeated roots, then you cannot write any of these things. But overall, if you have if gx has simple zeros, then Dirac of gx I'm written as 1 upon g dash xi mod Dirac of x minus xi. See how beautiful it is, because here it was x, here it was gx, here it is x. So such questions these days are being asked in the examinations. That is why I wanted to tell you. So for example, you will never find such expression. Never. मतलब तुमको दिखेगा ही नहीं, कहीं पर भी तुम try करना. Try to find this thing. It is meaningless. Why it is meaningless? I've already told you. All these things that I'm writing is only valid for simple zeros. X square has multiple zeros at x equals. So this becomes meaningless. Okay. So I hope to continue in the next session.